Okay, welcome to the problem session. Do you have any questions before I start? Would you like to have explanation of some topic or anything? Since we did not do too many examples on eigenvalues, I will start with eigenvalues and what we covered today. If any time left, we will go back to the old topics as well. So let's say we have a simple matrix A, minus 1, 1, 1, minus 1, let's say. Okay. Find the eigenvalues. And the corresponding eigenvectors. Why do I always say eigenvalues and the corresponding eigenvectors? Because they come in pairs, isn't it? So we are looking for the solution of this equation. Lambda and x that satisfy this. So therefore, for a lambda that makes this matrix singular, you are able to find, for that lambda, you are able to find an x. Okay, so that's the idea why I keep saying find the eigenvalues and corresponding eigenvectors. Okay, then we will say find the solution of this system of linear differential equation where x0 is given, let's say, as 1, 1. Okay. So how do we find this? What should I do? How do I go about this? Any idea? Yes.
How can x equals to 8 times x? I don't understand.
You don't understand this? I talked about this before. You remember? This is how eigenvalues and eigenvectors came into the picture. Okay? So you remember we said, you were there, I remember. We said x dot equal to ax. x0, let's say, is equal to 1. And how do I solve this? I said we just guess a solution like this. xt is equal to e to the lambda t c. You remember? Now you remember this? Should I repeat it again? But just since I started this, so we said we just take derivative of this. It is lambda e to the lambda t c. Substitute that here, you have lambda e to the lambda t c is equal to a e to the lambda t c. So this is xt, and this is x dot t. So what we are guessing a form of the solution, right? We are saying that can you find a lambda and the c such that when you substitute in the differential equation, it will satisfy it. So what did we find out here? So e to the lambda t is common in both sides. Since it is always greater than 0, you can cancel it. Then you have lambda c is equal to ac. When can this be satisfied? You have to have c equal to 0, right? Can you have c equal to 0? Why not? Because you will not be able to satisfy the initial condition. Then that means the solution is 0. So 0, x equal to 0, of course, satisfies the differential equation. But you cannot solve the entire problem. You cannot solve the initial value problem. Therefore, c is not equal to, so what do you have then? C is not different. C is different from, then lambda should be equal to a. Okay? Then we said xt is equal to e to the a, t, and c. So how do I pick c? For the initial condition, right? x0 says should be equal to 1, so substitute 0 here. So e to the a times 0 times c should be equal to 1. So e to the 0 is 1. So c should be equal to 1. Therefore, the entire solution is xt e to the a t. Satisfies the initial condition and satisfies the differential equation. Then we said, what if it is a matrix differential equation? Meaning xt in this case is several variables, right? x1t, x2t, xn t. If it is like that, and A is an n by n matrix, right? So how can we find the solution? The way to find the solution is we said, let's say, guess the solution as e to the lambda t times some vector. Okay? So this is again vector. So x dot t is equal to lambda e to the lambda t times c. So when you substitute that in the differential equation, then you have lambda e to the lambda t c is equal to a e to the lambda t c. C is a vector, okay? A is a matrix. So e to the lambda t cancels, so you have lambda c should be equal to ac. Again, when can you satisfy this? You can pick, we are looking for lambda and the c, right? Two things at the same time. So you can take c equal to 0. Again, this trivial solution. It will satisfy the differential equation. You will have xt equal to 0. But you will not be able to satisfy the initial condition. So therefore, c equal to 0 is out of question. But then in that case, what is lambda and how do I pick c? So it is a bit different from the other one, right? So I bring them to the same side, say ac minus lambda I c is equal to 0, right? Or just taking common with c, a minus lambda I times c is equal to 0. That's how we came up with eigenvalues and eigenvectors. We said that for this to be satisfied, so we need to solve for two things, right? This is a nonlinear equation. It's not a linear system of equation as it is. Right? We said we used our knowledge for matrices and null space of matrices, etc. So you have a vector here multiplying a matrix, and the multiplication is 0 without c being 0, without c being equal to 0. So what does that tell us? That tells us that this a minus lambda I must be singular. So you pick the lambdas that make this singular. So singular means, one way of saying singular is the determinant is equal to 0. So for which values of lambda this determinant is 0. Okay? So those are called eigenvalues. Okay, these are eigenvalues. So after you find the lambda that makes this 0, then you have a singular matrix. Let's call that I and Ci. So how many solutions does this have? If it is A is an n by n matrix, as we discovered, this is equivalent to an nth order polynomial. So an nth order polynomial will have n roots. This is fundamental theorem of algebra. It will have n roots. For every root of that polynomial, this determinant is 0. Therefore, you have a singular matrix. Therefore, this has a null space. Okay? So for that lambda I find Ci. If lambda has multiplicity more than 1, then what are you going to have? This will have a null space with dimension higher than 1. Then you will look for vectors that span that null space. Okay? That's how it was. Of course, after I find, let me go back to the differential equation. Let's say I found lambda 1, C1. These are pairs, right? Lambda 2, C2. Lambda n, Cn. So I was looking for one solution for this. Then I found how many? All of these. I found all of these. Each one of these satisfies the differential equation. These are like spanning vectors. So if each one of these satisfies the differential equation, their linear combination will also satisfy it, right? So you will have, so x t will be equal to, let's say, alpha 1 e to the lambda 1 t c1 plus alpha 2 e to the lambda 2 t c2 alpha n e to the lambda n t cn. Do we know what is c1, c2, cn are at this point? Yes, they are eigenvectors, so we know them. Do we know lambda 1, lambda 2, lambda n? Eigenvalues, so we know. So what are the parameters? Alpha 1, alpha 2, alpha n. How do I find this alpha 1, alpha 2, alpha n? Initial conditions, right? So when you substitute x0 is equal to alpha 1 c1 plus alpha 2 c2 alpha n cn, this should be equal to your x0. So you will find, so when you look at this, since this and A is n by n matrix, so this C1, C2, Cn, these are going to be in Rn, right? So what you are going to have here is C1, C2, Cn times alpha 1, alpha 2, alpha n equal to x0. So this is really a matrix. So you are trying to solve a system of linear equations. The entire problem is reduced down to finding solution of a system of linear equation to satisfy the initial conditions. Okay? So these columns, these are the eigenvectors. Of course, you will learn about these things in system theory courses and automatic control courses, signal processing courses. So we talk about these topics in detail. Okay. What else did we say? When t goes to infinity, what is this solution, by the way? This solution is a solution that gets all its energy from the initial conditions, right? There is no other input. You just have initial values of your xt, whatever that is. It could be a position, or it could be energy of a capacitor, or capacitors, inductors. It could be many physical variables. So what we are saying is that initially this has some initial conditions. What happens to this as t develops to infinity? So for a stable system, what do you expect? It should go to 0, right? So for that to happen, what would we need? You remember we talked about that? When t goes to infinity, meaning when t grows larger and larger, you don't want xt go to infinity. You don't want this, right? If it does, what is this? This is just from initial condition, it is exploding towards infinity. You want it to die down. For that, what do you need? You need eigenvalues to be negative, really more precise. Real parts of, since eigenvalues can be also complex, you want real part of lambda i's should be less than 0. Okay? Okay, so this is a quick review. I'm glad you brought it up. So I think it's important that we, from time to time, we go back and realize what is all these eigenvalues about, right? We talk about eigenvalues, so where is it originating from? Of course, in difference equation also we talked about that. Okay. So, is it stable? Is it a stable system? Okay. So what do I need to do here now? I need to find the eigenvalues, right? So let me erase. Okay, there is no need to erase that one. A minus lambda I is equal to minus 1, 1, 1 minus 1 minus 1, 0, 0, 1 times lambda. Okay, so that is equal to minus 1 minus lambda 1, 1 minus 1 minus lambda. Okay, so you take determinant of that. I'm sorry. Set that equal to 0. So what is the determinant equal to? Lambda plus 1 squared minus 1 is equal to 0. So this tells you lambda plus 1 squared is equal to 1. So lambda plus 1 is equal to minus or plus 1. So put here 1 and 2. So lambda 1 is 2. Lambda 2 is equal to, so lambda 1 is 0. Lambda 2 is equal to minus 2, right? So they should add up to minus 2. And their multiplication should be equal to what? Determinant. So what is the determinant here? 1 minus 1 is 0. So it checks. Okay. So let's find, we found now the eigenvalues. Let's find the eigenvectors. For lambda equal to 0, what is A minus lambda I? That's equal to minus 1, 1, 1 minus 1. Okay, so what is the solution for this? Can you just 1, 1, right? So x is equal to 1, 1 is a solution for this. Okay. By the way, is this Hermitian? Yes, it's systematic. So we expect that both eigenvalues will be real. Okay? So for lambda equal to 1, A minus lambda I is equal to, so minus 2, minus 2, it is minus 3, 1, 1, minus 3. So A minus, this is lambda 2. Huh? It's, of course, it is, yes, 1. Very good. You should correct me. It's always, one can always make errors, okay? So what is then A minus lambda 2I times x1, x2, that's equal to 1, 1, 1, 1, x1, x2, so that's equal to 0, 0. So what should this be? Very easily, 1 minus 1 or minus 1, 1. So we have both. So then A times, so let's call this x1, let's call this x2. x1, x2 is equal to x1, x2, lambda 1 0, 0, 0, lambda 2 is minus 2, right? So A times, this is 1, 1, 1 minus 1, 1, 1, 1 minus 1, 0, 0, 0, minus 2. As a matter of fact, if we scale this and make them orthonormal, and we should, isn't it? So here. Then the columns are orthonormal. And then what do we know? So let's call this x is equal to 1 over square root of 2, 1, 1, 1 minus 1. So x star, x star is equal to identity, of course, right? Since this happens to be a Hermitian matrix. Let's verify this. Okay, what is x? So x star x is equal to 1 over square root of 2. Why did I divide by 1 over square root of 2? I normalized my vectors, column vectors. So column vectors have length 1. This is Gram-Schmidt orthogonalization. So this is star means transpose, since there is no complex element, just 1, 1, 1 minus 1 into x 1, 1, 1 minus 1 times 1 over square root of 2. So what would I have? This 2 is 2. This 0, 0, and 2, and this 2 square root of 2 gives you this. So it is 1, 0, 0, 1. Of course, here I did not use Gram-Schmidt. Why, Husni? Why didn't I use it? They are necessarily orthogonal. Why? Because their eigenvectors correspond to distinct eigenvalues of a Hermitian matrix. So therefore, they necessarily are orthogonal. So you don't need to orthogonalize them. When would you need to orthogonalize them? If you had a multiple eigenvalue for a Hermitian matrix, then you would have more than one vector spanning that that subspace, okay? Then you would just take any two and find the orthogonal pair that spans the same subspace, okay? Okay, so we solved this. Is this system stable, okay? So if I were solving this with that A, okay? Let's say x0 is 1, 1, okay? What would be my solution? The solution would be, let's just directly write it. It will be e to the lambda 1t. So what is that? E to the 0t. What is the eigenvector for that? What was it? 1, 1. Okay? So 1 over square root of 2. What am I going to take here? Alpha times this, right? Let's say alpha 1 times this, plus alpha 2 times, what is the other one? E to the minus 2t. And the eigenvector? 1 minus 1, 1 over square root of 2, and alpha 2, right? What is e to the 0t? It is just 1. So you have alpha 1. So I will just incorporate this and this together. I will call it alpha, okay? Since we are solving for it. Or let me call it beta. Beta 1 times 1, 1, plus beta 2 times 1 minus 1, e to the minus 2. 2t. Okay, this is the solution of this differential equation with that a. Now let me satisfy the initial condition. So x0 should be equal to, we said 1, 1, and that should be equal to beta 1, 1, 1 plus beta 2, 1 minus 1. In other words, one, 1 minus 1 times beta 1, beta 2 should be equal to 1, 1. Just by coincidence. So what is beta 1 and beta 2? Beta 1 is equal to 1. Beta 2 is equal to 0. So the solution that satisfies the differential equation and satisfies the initial condition in the end is xt is equal to 1, 1. That's it. Constant. There is no t in it. Okay? Because lambda 1 was equal to 0. Okay, that's the reason. Yes. But so what if, let's ask the question, what if x0 was 1, 0? Okay? So let's try to find a solution for this. Okay? So let's just, so t didn't appear in the solution, it doesn't look nice. Okay, in that case, what would this be? 1, 1, 1 minus 1 would be beta 1, beta 2 would be equal to 1, 0. So that would give you just, we can solve this in 1,000,000 different ways, right? Let's do the one that we love most, all of us now in this course. You subtract this from this, so you have 1, 1, 1, you have 0, then this is minus 2, and this is minus 1. So this gives you minus 2 beta 2 is equal to minus 1, beta 2 is equal to 1/2. So beta 1 plus beta 2 is equal to 1. So beta 1 plus 1/2 is 1. So that means beta 1 is equal to 1/2. So that gives you then xt is equal to 1/2 times 1, 1 plus 1/2 times e to the minus 2t 1 minus 1. Okay? That satisfies this initial condition and satisfies the differential equation. Isn't that nice? Is this stable? Yes, this is on the border of stability. Okay? So to have really stable means with initial conditions, when t goes to infinity, the xt should go to 0. But this is, at least it's not going to infinity, but it's staying finite. So this still requires infinite amount of energy. When you consider it, keeping something up here all the time till infinity requires some energy. But this is conditionally stable. For some inputs, this will blow up. Okay? Okay, so this gave you in a very simple example, we covered a lot of things, right? We found eigenvalues, eigenvectors. We found also the solution of system of linear differential equations. So we covered quite a bit of things. Yes?
About xt is equal to 1, 1 in order to stabilization.
Stabilization, this is what I said. It is not unstable. It is in the border of stability. So lambda equal to 0, okay? Lambda equal to 0. If lambda was negative, then when t goes to infinity, as you see here, with starting from other initial conditions, when t goes to infinity, this immediately dies out. After a few seconds, the contribution of this second eigenvector is zilch. It just goes to 0. The first one remains as it is. It never dies out, okay? So it is, this kind of systems are marginally stable systems, we call them, okay? So we don't prefer them. When we design systems, they are not like this. So we want our system to respond to the input. We don't want our system to behave according to what it has initially. So we don't want initial conditions of a system to define or determine what our system does, because we have no control over initial conditions. Initial conditions of a system are mostly unknown. They are not within our control. But as engineers, we have a control over what goes into the system. So therefore, we don't want the initial conditions to appear in the output like this. Okay, we want them to die out. Okay, any other questions? So I don't want to get too much into system theory here. It's linear algebra. But you are now ready with these things. You are now ready to learn all those things in circuits and systems and many things. This is the really basis of that. Yes?
So what did we find now?
What did we?
Generally find.
Where in this one? We found the eigenvalues of this. We found the answer of the question. We were asked to find the eigenvalues of this matrix and the eigenvectors of this matrix. We found them, right? Do you realize that we find them?
Actually, I think that we found these things in up eight.
Yes, we did. Then we said that find the solution of, is this stable? Is this differential equation stable with these initial conditions, okay? So we found the solution of the differential equation as well. It's a part of, so we will have questions like this so that you develop into the solution, okay? Let me ask you another question about this. I would like you to find what is a to the 57, or I might just make it more tricky. I ask you what is a to the 4, okay? If I ask you what is a to the 4, okay, if you spend half an hour and multiply this a, one and one more, you can still get the right answer, but you will lose at least 15 minutes. If I am more merciful, I will ask you for a to the 400, so you will say that, no, I cannot multiply a to the 4. But this is tricky, so if I ask you a to the 4, you will say, okay, let me multiply this 4 times. Of course, you should immediately realize that professor is not asking me to multiply this matrix 4 times, right? So how do I find this? So this is a is equal to x gamma x inverse, right? Of course, in this case, x star. So this to the 4 means this is x. That's it. So this is going to give you, in this case, what is x? X was 1, 1, 1 minus 1, 1 over square root of 2. Then you have here 0 to the 4 minus 2 to the 4, 0, 0. And you have here 1, 1, 1 minus 1, 1 over square root of it's transpose it equal to itself. Okay. So what is minus 2 to the 4? 16. So this is 0 and this is 16. So you can just multiply it out, or you can leave it like this, right? So this is the 4th power of this a. Okay? Yes?
Do we have to normalize the vector x?
If you normalize it, then the transpose of it is equal to its inverse. Yes, for Hermitian matrices, you should normalize it. Because you lose a lot if you don't normalize it. Okay, you lose a lot. Yes? So properties of Hermitian matrices. So Hermitian matrix means A is equal to A star, meaning A star is A transpose conjugate. Okay? So first property is that Hermitian matrices have real eigenvalues. Two, if lambda I is different from lambda j, then let's say this is x, this is y eigenvectors. Corresponding to these, then you have x orthogonal to y. 3, Hermitian matrices, these two we proved. Hermitian matrices always will have a full set of n eigenvectors. And I will say orthogonal, okay? You know what I mean. I explained that several times today, okay? So that means that, so this 3 means a Hermitian matrix can be written like this, U1, U2, Un. Call this U times U lambda, okay? So AU is equal to U lambda. In other words, A is equal to U lambda U star. So U star U for a Hermitian matrix is equal to identity. This is very important. And the reverse of this is that lambda is equal to U star AU. Okay, this is very, very valuable for us. Okay? Of course, using these properties, we defined singular values and many other things. Okay, this is extremely useful. And we talked about positive definite matrices. Another way, the solution for this, I will now tell you about this again, okay? You will see that in the book and in many places, they talk about this as follows as well. Let's look for a solution in this form. Okay? E to the AT. So matrix goes into exponent of AT. Okay? What does this mean? So let's call the derivative of this as, so you take derivative of this similar to the usual exponential function we know. This is A e to the AT times C, okay? You substitute in here, you have A e to the AT C is equal to A times e to the A, T, and C. Okay? This A to the e to the AT, you have in both sides. Okay? So you have A e to the AT, A e to the AT, and C in both sides. So it satisfies it, right? So what is e to the AT? E to the AT is what we found there. But let's look at it in a formal way. So e to the AT is defined like this. E to the AT, the scalar function. You remember I talked about this when I defined e to the I theta. Remember? So for that I developed this. This is equal to 1 plus AT over 1 factorial plus AT squared over 2 factorial AT to the power n over n factorial. Okay? So from this, we generalize this. E to the AT means, okay? I'm not saying gonna say equal. This means, okay? This means identity plus AT plus AT square over 2 factorial AT to the power n divided by n factorial, and it continues like that. This is what it means. Okay? So now let's say, what does AT square mean? We know this is matrix multiplication. So AT is a scalar, so T squared times A times A. That's what it means, right? So if you have eigenvalue decomposition of the matrix, then what would that mean? That would mean A equal to X, gamma, X inverse, isn't it? So A square is X, lambda square, X inverse. A to the power n is X, lambda to the n, X inverse. Right? So you substitute this in here, you have e to the AT is equal to I plus T X lambda X inverse plus T square X lambda square X inverse over 2 factorial plus etc. T to the power n over n factorial X lambda to the n X inverse, and continues like that. Okay? So this X inverse exists in all of them. As a result, it's also here, right? I can write identity as X times X inverse. Therefore, I can take common here. So this is X, parenthesis, identity plus T lambda plus T squared over 2 factorial lambda square T to the power n over n factorial lambda to the power n plus X inverse. So when you look at this lambda, since it is diagonal, what do you have there? So this is a diagonal matrix, 1 plus T times lambda 1 plus T squared over 2 lambda 1 squared, right? All the way T lambda 1 to the power n over n factorial, and then next term is 0, like this is 0. What is the second term here? 1 plus lambda 2t over 1 factorial plus lambda 2t square over 2 factorial, etc. What are these? As a scalar function, what is this? Isn't this e to the lambda 1t? Isn't this Taylor series expansion? Of course, you didn't finish your calculus yet, right? Did you take your calculus 1? Did they talk about Taylor series? Not yet. But I talked about it. So this is e to the lambda 1t. This is e to the lambda 2t, okay? Etc. So you will have e to the at is equal to x e to the lambda 1 t 0, 0, 0 e to the lambda 2 t 0, 0, 0 e to the lambda 3 t 0. Okay? So you have this diagonal matrix times x inverse. Okay? So this is e to the at. This is how you form it. As a matter of fact, yes. X is in the other side. So you should always close the parentheses, you are saying, right? Yeah, here. That's where it is. No problem. Yeah.
Can we consider this solution as a concentrated version of this, the previous one?
Yeah, they are the same thing. They are basically, you see the eigenvectors come into the picture here as well, right? It's the same thing, okay? But the other one is, I didn't have to define matrix exponential function, right? It just naturally I explained it to you. Okay? So they are the same thing. So I prefer the other one, but it's also, of course, this opens a door for defining for anything, right? You can talk about sine of AT, cosine of AT. Okay? You can talk about any weird thing. You can talk about what? Logarithm of AT, anything. How do you talk about it? You talk about the scalar function. You take the Taylor series expansion of the scalar function, then you place there your variable with the matrix. Okay, of course there are conditions. It's not as simple as this. When would that converge? When would that this function make sense? If all of the eigenvalues, absolute values of the eigenvalues of A are smaller or are within the range of the radius of convergence of that function. That wouldn't make sense, a lot of sense to you, but this is not unconditional. But as far as e to the at is concerned, since this series is convergent for any x, right? We said for any x, e to the x less than infinity is convergent. Therefore, it is valid for any a. But this wouldn't be valid for any a. This would be valid, but this is not a matter of this course. So this is again a separate topic, but in the book it is talked about, and maybe your friends will tell you that we learned about e to the at, and did your guy tell you about e to the at? So here it is. I mean, it's nothing else. It's this. Okay? Okay. Let me talk about a little bit more about similarity transformation, okay? So let's say similarity transformation. So you say you have a matrix A, and you go to T, A, T inverse. Okay, so let's call the matrix B. So use the matrix T and transform, go from A to B. Okay, just A and B are two square matrices, and T is a non-singular matrix, so that you have inverse of it. Okay, what is the relationship between these A and B? Okay, let's look at the eigenvalues of A. So eigenvalues of A are determined by A minus lambda I. Determinant has to be equal to 0. Okay? What are the eigenvalues of B? B minus lambda I. Determinant is equal to 0. What is the relationship to lambdas? Let's call this mu so that you don't necessarily think they are the same. Okay? So these are the eigenvalues of A, these are the eigenvalues of B. But we have such a relationship between A and B. Okay? Let's now find out what these eigenvalues are. So B minus mu I is equal to what? T A T inverse minus mu I, right? Determinant. So since this is just an identity, I can do the following. T A minus mu I T inverse. So what is this equal to? You have three matrices here, right? 1, 2, and 3. So what is the determinant of this? Times determinant of A minus mu I times determinant of T inverse. Okay? What happens? These two cancel, right? Determinant of T inverse is 1 over the determinant of T. Okay. How do we know that? T times T inverse is equal to identity. You just take determinant of this. So determinant of T inverse is equal to 1. So that's it. Determinant of T inverse is equal to 1 over determinant of T. For this is an easy exam question, isn't it? Very easy, just 5-second answer. If you know it, you just do it immediately. Okay. So when you set this equal to 0, what did we find out? So eigenvalues of B, we call them mu, but it turns out that they are nothing but lambda. So this means lambda is equal to mu. That means eigenvalues of are invariant under similarity transformation. Eigenvalues of a matrix do not change when you perform a similarity transformation. Isn't that a beautiful property? So eigenvalues are invariant under similarity transformation. Okay, what happens to eigenvectors? So you have the eigenvectors of eigenvalues of A are Ax is equal to lambda x, right? So eigenvectors of B are By is equal to lambda y. We know that now. We now know that they are the same. Okay. From here, let's continue. What is B? T A T inverse times y is equal to lambda y. Okay, let me just multiply with T inverse from here. What do I get? A T inverse y is equal to lambda T inverse y. Okay, let's call this Z, or should I call it X? So eigenvalues of B is equal to TA T inverse are equal to T times X, where X is T inverse times where X is an eigenvalue of A. Okay. Since we already have an example, to save time, we already calculated the eigenvalues of a matrix. Right? Let's make a similarity transformation on that and see what happens to the eigenvalues and eigenvectors for that matrix. we start from matrix A and find the eigenvalues and eigenvectors, we'll spend a lot of time. So A was equal to, what was it? 1, 1, 1, minus 1, if I'm not wrong, right? And x1 was 1, 1, 1 over square root of 2. x2 was 1, minus 1, 1 over square root of 2. Okay? Excuse me?
On the top left one,
Here.
Yeah.
Okay, good. Thank you very much. Okay, so let's make a simulated transformation on this. Let's take a simulated transformation. Let's say 1, 2, 1, 1. Okay, any matrix. What is T inverse? T inverse is, determinant is 1, minus 2, which is minus 1, okay? Okay. I will make this 2 and this 1 so that I don't deal with minus, okay? So determinant is 1, so therefore 1 over determinant, so it remains the same. So it is 1, so this is 2, and this is 1. They exchange and their sign changes, okay? So what we are saying is that T inverse, so 1, 1, 1, 2 times A minus 1, 1, 1 minus 1 times 2 minus 1, minus 1, 1 has the same eigenvalues. This is lambda equal to 0. This is lambda equal to minus 2. It has the same eigenvalues as this one. And it has eigenvectors are equal to 2 minus 1, minus 1, 1 times 1, 1, 1 over square root of 2. And the other one is 2 minus 1, minus 1, 1 times 1 minus 1, 1 over square root of 2. So these are the two eigenvectors of this matrix. So let's see if that is the case. Okay? By the way, what is this equal to? Let's do the multiplication. So it is 2 minus 1 is 1, minus 1 plus 1, this is 0, times 1 over square root of 2. And this is 2, so this becomes 3. And this is minus 1, this becomes minus 2 times 1 over square root of 2. Okay? Let's multiply this out. So this is minus 1 plus 1, this is 0, 1, and minus 1, this is 0, right? And this is minus 1 plus 2, this is 1, and this is 1 minus 2, this is minus 1. It's so lucky, right? We have such a nice number. So that's equal to 0, 0, and this is equal to 1. So this is, excuse me, 2, no, this is 3. This is 3, and this is minus 1, that is minus 2. So you see, this is now T inverse, right? What are the eigenvalues? It is 0 and minus T. You see that, right? It's immediately, it's there. Okay? So eigenvalues are, this means we didn't make a calculation error. We are not trying to prove the theorem by examples, right? There is no such thing. So unfortunately, some of you do that in the exams. They try to prove. I ask, for example, a property. They try to prove it by just cooking up a 2-by-2 example. That's not how you prove theorems. eigenvalues are lambda 1 is equal to 0, lambda 2 is equal to -2 as expected. And eigenvectors, so this is minus lambda 0, 3, -2 minus lambda times x1, x2. So for lambda equal to 0, minus lambda, right? Lambda equal to 0, this is, so what do you have? 3x1 is equal to 2x2. So if you take x2 equal to 1, this is 2 and 3. Is this true? Why is it -2? I made a mistake somewhere, right? Or I made a mistake there. So I didn't make a mistake there. Please find the mistake. So there is no mistake there, then mistake should be there. Oh, no, it's not. There is no mistake, right? This is, huh? It should be? X2 is 1. Okay. If x2 is if you take x2 equal to 1, what do you get? x1 is 2 over 3, right? So where did I make a mistake? Yeah. If x2 is 1, then x1 is 2 over 3. 2 over 3. Right? So you multiply by 3, so there is an error somewhere. You find it out. Oh, there, this is the one. Is this the one? This corresponds to 0, right? So there's an error somewhere. Okay. So we don't want to spend half an hour more on this. Please investigate and tell me. Okay? I will also look it up. Let's say we have a matrix A is equal to 1, 2, -1. Of course, a Hermitian matrix. 2, 5, 1. Then this is -1. This is 1. And this, let's say it's 2. Okay? Is a positive definite matrix. Okay? How would you go about this? I prefer Gaussian elimination from double side, Cholesky decomposition. Okay? Let's just go through that. So 1, 2, -1, 2, 5, 1, -1, 1, 2. This is a symmetric matrix, right? The idea is the following. I make a row operation on this, and I go to this one. So twice this is subtracted from here, right? So let me just keep track of it here. So L21 is equal to 2. So you subtract 1, 2, -1. This becomes 0. This becomes 1. Twice this is subtracted from this means 1 minus -2. That is 3. Okay? So twice, so this -1 times this is subtracted from here. So L31 is equal to -1. So this is 0. Basically, you add these three. Right? There is 3 and this is 1. Okay, from here, one more step. 1, 2, minus 1, 0, 1, 3, 0. So this is my second pivot. This becomes 0. 3 times this is subtracted from here, right? This becomes minus 8. Now what I do is the following. I do, this is now L32 is equal to 3. Whatever I did here, I will take 1 times the first column, subtract from the second column, okay? And minus 1 times first column will be subtracted from the third column, okay? As you see, it doesn't change anything here, okay? So this, now I go column-wise. So this becomes 1, 0, 0, 0, 1, 0, 0, 0, 8. This is so beautiful, okay? There is no need to further elongate it. And it turns out that 1, 2, minus 1, 2, 5, 1, minus 1, 1, 2 is equal to L, this 1, 0, 0, 0, 1, 0, 0, 0, 8 times L transpose. Isn't that very beautiful? Yes?
I didn't understand.
Of course. It's amazing, isn't it? It just comes out, just very beautiful result. I discovered this 3 a.m. in the morning, and I said, oh, good. Then the following day, I found out it was done 101 years ago by Cholsky. So this is, we are performing here, okay, our Gaussian elimination, right? What does it mean? Let me just do this in matrix. So what is this L, by the way? This is 1, 0, 0. This is 2, 1, 0, minus 1, 3, 1, right? The usual, you know this. So there is nothing extra. When you have a symmetric matrix, you automatically have this. Instead of having LU, you have LD, L transpose. Okay? And these are the pivots. For positive definiteness, what you need is that this pivot should be positive. As a matter of fact, this is how you prove that second test, or what was it, the last test? The pivot test for positive definiteness. I gave it to you without proof this afternoon, right? So this is really proof of that. So the pivots, since you see, when you talk about quadratic form, like this X transpose L and D and L transpose and X, this is like Z transpose and Z, right? I'm sorry. Technology accident. This never happened, right, before? Okay, so Z transpose Z. So the only way, this is like that Hermitian matrix case, right? These are not eigenvalues, by the way. But the only way this can be negative is if any one of these is negative. So in this case, minus 8. So how would you pick your Z? You would pick it so that all these are killed. So it's 0, 0, 1. So you would pick this, the Z is equal to 0, 0, 1. Then it would give you minus 8, this quadratic form. So therefore, it is. Of course, I didn't forget about your question. We will go through it, okay? We will go through it. Okay, let's just discover it. How is it happening? Yes?
Do we do not need to state what are the multipliers in doing column operations? Like you did in the rows L21 is 2.
I did. These are
In like column-wise.
column-wise, yes, but it's the same thing. So let me do that also, okay? Since this is a symmetric matrix, this is possible. Otherwise, it's not possible, of course. Whenever you are doing something, we are breaking the symmetry here, right? I said, why should we break the symmetry? Why? Let's preserve it. Whatever we do here, we can do the same thing on the columns. And it doesn't change the determinant, right? Column operations do not change the determinant. If you take a linear multiple of a column and subtract it from another column, or if you take linear multiplication of a row and subtract from another row, it does not change the determinant. So therefore, use this property. So let's see what's happening here in this example. Okay, so at that point, when we have this, okay, 1, 2, minus 1, 0, 1, 3, 0, 0, minus 8, okay? Now let's perform column operations, okay? So what are we going to do? We will multiply this row with 2 and subtract it from here, right? That corresponds to exactly doing this L transpose thing, okay? So what this means is that so one, I don't want to confuse you. So that means, so 1, 0, and this, of course, has no effect. These are all 0 already, right? So this means also to add this column to this. That also gives you this. This 0, and this is 1, 3, and this is 0, 0, 8. So at this point, what do? You just multiply this by 3 and subtract it from here. So 1, 0, 0, 0, 1, 0, 0, 0, minus 8. Okay, this is minus 8. This is what it is. As a matter of fact, if just take this 1, 2, minus 1, 0, 1, 3, 0, 0, minus 8, and multiply it with L transpose. So what is L transpose? 1, 2, minus 1, 0, 1, 3, and 0, 0, 1, right? What does this give you? This is 1, right? And this is 2 plus 2, it is 4, right? And this is minus 1 plus 6, 5, and this is minus 1, that is 4. So if you multiply this together, okay, you find out that it just boils down to, it gives you back A, okay? So this is 0, and this is 0, and this is 2 and 3, this is 5, and this is minus 1, and this is 9, this is 8, and this is minus 8, and this is 0, right? And so I should go step by step on that. Let's do the verification of it. So L is 1, 2, minus 1, 0, 1, 3, 0, 0, 1 times 1, 0, 0, 0, 1, 0, 0, 0, minus 8 into 1, 2, minus 1, 0, 1, 3, 0, 0, and 1. Okay? So this is the same matrix, except that this is multiplied by minus 8. This is what it means. This first multiplies the first column by 1. This multiplies second column by 1. This multiplies third column by -8. So when you multiply these two together, 1, and this is 2, and this is -1. This is 2, and this is 4. This is 5, and this is -2 plus 3 is 1. This is -1 times, so this is -1, and this -1 plus 3 is 2. -2 plus 3 is 1, and this is 1 plus 9 is 10, minus 8 is 2. So is this A? Okay. So this is, for this example, we proved that L transpose is true, and it's always true. Of course, provided that you can start this process. For example, let me give you a counter example. A is equal to 0, 1, 1, 0. Okay? Can you do Gaussian elimination on this? No. So what happens? It breaks down, right? But in this case, if you exchange the rows, let's say take A squared, this becomes 1, 0, 0, 1. This is inverse of itself. Okay? And then you can, this is already, of course, in L transpose form. So this is just D, right? There is identity. So there is no other operation needed. But like Gaussian elimination, if you have 0, 0 element, you get stuck. So here also you could get stuck. So why did we start talking about this? Pivots. We asked a question about, is A a positive definite matrix? Yes. You didn't need to do this. You could just stop here, okay? You don't need to have the diagram, but it doesn't, we just made this 0. It doesn't take any more calculation, okay? So since it is a Hermitian matrix, it's a diagonal, it's diagonalizable like this. Is this a similarity transformation? No. It is not a similarity transformation, okay? Of course, this has a certain property. It will leave the inertia of a matrix unchanged. Inertia means if a matrix has, let's say, a certain number of negative eigenvalues, certain number of positive eigenvalues, and certain number of zero eigenvalues. If you multiply with A with B and B transpose, or L transpose from right and left, it will not change the inertia, meaning the numbers will not change. Okay? So we use that in developing some things. Okay, what should we do next? These are the things. Oh, let's do a singular value decomposition. In singular value decomposition, the reason why it's very important, and I use singular value decomposition and those things a lot in my PhD thesis, so 30 years ago, it is extremely important. The reason is this. When we want to identify a system, or when we collect data from some process, millions of data pairs, or lots of amount of data comes to you from an image, from the space, or from wherever. And all this data gets spoiled with some noise, okay? And you don't know what is real data and what is noise. Okay, singular value decomposition, when you perform singular value decomposition, you might just have a matrix H, okay, that you are observing impulse response of a linear system, let's say, okay? You will get lots of data, H11, H12, H13, H1n, large amount of data, H21, H22, etc., etc. Okay? What will happen is that because of the noise in the measurements, like the problem we talked about before, AX equal to B, you will have rank of this will never die down. You will have, you want to find out whether you can write this like some A times B transpose, okay? You can write it down like 2 columns, 3 columns, okay? By 3 columns, let's say, 3 rows. This could be very long matrix, but you wanted 3 columns. So instead of having, let's say, this, if this is 1,000 by 1,000, okay? Here you would like to have 1,003 and 1,003. So what would this give you? 3,000 and 3,000. So how many data points you have? 6,000 data points, right? Instead of having 1 million data points, you can represent this data with 3,000 data points. How do we do that? So we do singular value decomposition of this matrix, okay? So what we do is that we say H is equal to some U sigma V transpose. And when you look at this sigma, it's going to be something like this. Sigma 1, the largest one, sigma 2, sigma n, okay? And in practice, this is how it's going to be. First one will be like 1,003. The other one will be 7. The other one will be 0.5. The other one will be 0.001. And then 0.10 to the minus whatever. You will see that after 2 singular values, the rest is really a result of the noise. It's not really the data. So this allows you to analyze your data and find out what really matters there. Okay, so what you do is that you do an approximation. You set all these to equal to 0, then it would mean that in this U, you would just take the first, if you just took first 2 singular values, you would take the first 2 columns of this and first 2 rows of this. That's it. That's why we said you have singular value decomposition for non-square matrices as well, right? So you can have, that would allow you to represent this matrix that has 1 million data points with, as I said here, with 6,000 data points, even maybe less. So therefore, this allows you to analyze your data and separate the noise from data. Okay, this is, in that sense, it's very important. But as far as this course is concerned, what you are supposed to do is that we give you a matrix A, and we ask you to perform the singular value decomposition for that matrix A. So let's do that. And probably you will have a singular value decomposition question in the exam. Most probably. Let's release a homework set this weekend so that they can prepare. Remind me. Okay. Let's say we have a matrix A is equal to 1, 1, minus 1, 1 minus 1, 1, times 1, 1, 2, 0, 1, 0. So that's all. Okay. 0. Okay. I will just make this 1, 0, 0. So what is this equal to? 2, 1, 2, 0, 1, 2, 0, minus 1, and minus 2. This is how you generate questions. So that I want to make sure that the rank here is 2. Okay? So it doesn't have full rank. If I start from here, it is difficult to organize the rank. But if we write it as multiplication of 2 matrices, you know that It cannot have rank more than 2. Okay? So find the singular value decomposition. Decomposition of A. Okay. Okay, how do I do that? So this is a symmetric matrix, so I don't have to worry about M and N and things like this, okay? So I am looking for A is equal to U sigma V transpose, right? So to get U and V, I do certain things. What were they? I say that AA transpose is equal to U sigma V transpose V sigma U transpose. This is identity, so this is U sigma square U transpose. So first thing to do is I calculate AA transpose and find eigenvalues of it and eigenvectors. So I perform this diagonalization, right? So what is AA transpose? AA transpose is 1, 1, minus 1, 1, minus 1, 1, 1, 1, 2, 1, 0, 0 times A transpose is 1, 1, 2, 1, 0, 0 times. Of course, you wouldn't notice that it's coming from here. 1, minus 1, 1. So this will give you 1, 2, or 6, and this will give you 1, and this will give you 1, and this will give you 1. Okay? And this is, of course, a lot of computation. This has to be done in computer normally, right? You don't do it by hand. That's why we give you very simple questions in the exam. So this is 6 plus 1 is 7. And this is 5 is minus 6 plus 1 is minus 5. This is 2. This is 0. And this is 0. And that gives us 9, 5, minus 5, 5. This is 5, minus 5. This is minus 5. This is minus 5. And this is 5. So it is it the Hermitian matrix? Yes. So I need to find the lambdas of this. So A minus lambda I. It's going to take too much time. I don't think you will be able to follow it. You are sleeping. So ask me questions or let me explain something to you. Please do this though, okay? So you try to solve this. This has, of course, this has rank 2, so one of the eigenvalues is lambda equal to 0. So we know one of the eigenvalues, therefore the other two are also, one of them is 0, the other two are real, and we should be able to find it. I will also solve it myself. And let's post this on the website. Any questions? I guess everybody is very tired, so I'm going to release a homework set, and you work over it and send us questions if you have any questions. Okay? Good luck in the exam.